All right, everybody, let's take a look at the Chapter 6 quiz, and hopefully it makes a little more sense after you see the solutions, okay? But if you still have questions, obviously reach out to me. Here we go. Question 1, a coin is flipped 3 times. Draw a tree diagram and use the diagram to find the probability that all heads or all tails will show up, okay? So if we flip a coin 3 times, what's the probability we get all heads or all tails? Let's figure that out. So on the first flip, we could get heads or tails. And the probability of each is 1/2. I'll just notate that for the first flip. On the second flip, we could get heads or tails. And on the last flip, we could get heads or tails. Okay, so there's our tree diagram representing 3 flips of the coin. We want all heads, that would be this path, or all tails, which would be this path. Okay, probability of getting all heads is going to be 1/2 times 1/2 times 1/2. Which is 1/2 cubed, or 1/8. Probability of all tails is exactly the same here. I'll write it like this time. And so adding those together, we get an overall probability of 2/8, or 1 out of 4. All right, so again, with the tree diagram, we can label the probabilities of the outcomes along the branches. And then to find the probability of any one particular path, we multiply those probabilities together. So there was the path of all heads, 1/2 times 1/2. Probability of all tails, 1/2 times 1/2, and then add those together to get the total probability of the outcome we're looking for. Okay. Number 2. Leonard has 1 nickel, 1 dime, and 1 quarter in his pocket. Leonard picks 1 coin at random. Without replacing the coin, he picks a second coin. Using the tree diagram drawn, what is the probability that the 2 coins picked have a sum of more than 20 cents? Okay, so they gave us the tree diagram. Now, if you want to throw the probabilities in, you can do so. We have a 1 in 3 shot of grabbing a nickel, a dime, or a quarter on the first draw. Just randomly reaching into our pocket, grabbing the first thing we touch. Then, regardless of what we get first, we have a 1 out of 2 probability for what we can draw second. If I get the nickel first, well, I have 2 coins now in my pocket, one of which is a dime, one of which is a quarter. Okay, and so here's our tree diagram with the probabilities. And if you think about it, if any single path has a probability of 1 out of 6, right? 1/3 times 1/2, every path has an equal probability of 1/6. So these are all equally likely to occur, any of these outcomes. So what we need to do then is just figure out, of all those 6 outcomes, how many of them are going to yield a sum of more than 20 cents. All right, so we got to figure out of those 6, how many are going to have a sum of more than 20 cents. Well, let's think about this. We should know what money's worth by this stage of the game, right? A nickel's 5 cents, a dime is 10 cents, this is 15 cents. Okay, so that's certainly not more than 20 cents. 5 cents in a quarter is 30 cents, so there's one path that leads to a sum of more than 20 cents. 10 in 5 is 15. 10 and 25 is 35, so that works. A quarter by itself is more than 20 cents, so both of these should work. But here we have, what, 30 cents with a quarter and a nickel, 35 cents with a quarter and a dime. So it looks like out of those 6, 4 of them are going to yield a sum of more than 20 cents. And if we simplify that, we get a fraction of 2/3 back. Choice D. All right, a bed and breakfast offers a dinner that consists of 1 of 3 main courses and 1 of 3 desserts. If choices are equally popular, what is the probability that someone will order roast beef and pi. All right, so looking at the main courses here, it looks like roast beef constitutes 1 out of 3 of those choices. And someone will order pie. Well, if we look at the desserts carefully, it looks like there's 2 types of pies out of the 3. So there's a 2/3 probability that someone will order pie. And so the probability, I'll notate it like this: roast beef and pie will be given by the product 1/3 times 2/3, which is 2/9 probability. Okay, or if you punch that in, 0.222 repeating is fine as well. Okay, but there you have it. Again, when events are independent, to find the probability of the and situation, you're simply multiplying those probabilities together, okay, provided events are independent. Number 4, the student population of Richmond High School this year is given in the table. If a student is selected at random from the school, find the probability that the student is a grade 12 student. Okay, well, let's take a look. How many grade 12 students are there? Okay, well, it looks like total there are 400. That's the number of total grade 12 students. So the probability that we selected grade 12 student is going to be 400 out of the total number of students, which is that 1100. And that simplifies to 4 over 11, which is choice A. Okay, question 5, kind of testing your knowledge of the notation here. Let A represent the event that a card drawn is red. Let B represent the event that a card drawn is a 4. What does P parenthesis A and B with the line over it represent? Okay, so basically this is what it represents: the probability of A and not B. Right, the line over the letter B is known as the complement of event B, or not B, the opposite of B. Okay, so in words, this is the probability of event A and not B. And what was event A? Event A is the card drawn is red, so the probability of getting a red card and not, let's see, let B be the event the card is a 4, so not a 4. I'm looking for probability of red and not a 4, and you got to look carefully. A looks close to that. Probability the card drawn is red or not a 4. That's not what we're looking for. We're looking for choice B, red and not a 4. Okay, number 6, perhaps one of the toughest mathematically speaking here. This is Bayes' theorem. A medical test for leukemia is 97% accurate. That means that real positives are 7% accurate. False positives are happen 3% of the time. Okay, but on the flip side of that, true negatives will show up 90% of the time, and false negatives will show up 3% of the time. Suppose that 0.6% of the population have leukemia. What is the probability that a person who tests positive does have leukemia? So let's have some notation here, okay? I'm going to use the plus symbol for tests positive. Very similar to what I've used in the examples that we've done. Here will be tests negative. Okay, and I'll use the letter L to represent has leukemia, and not L for does not have leukemia. Okay, so pretty similar notation. I use D and not D for disease, not disease, when I've done examples like these before. Okay, but I'm just using the letter L for this problem. Okay, so look, we can go through this a couple different ways. Let's start by notating some things here with probability. Suppose that 0.6% of the population has leukemia. So the probability a randomly selected person has leukemia is 0.6%. So look, don't forget to move the decimal over. That's really 0.006 as a number, as a decimal. Okay, so be careful with that. So from that, we can take that the probability somebody doesn't is the remaining 99.4% because those are complements, right? So they got to add up to 1. Now, in terms of the test being 97% accurate, okay, that's the probability the test comes back positive given you have the disease. The probability the test comes back positive given you have the disease that's 97% accurate, okay? And the probability the test comes back negative given you have the disease will be the other 3%. Now at the same time, if it's 97% accurate, it's going to be 97% accurate with the negatives. So we all, whoops, scrolled in inadvertently. Here we go. So the probability the test comes back negative given you don't have the disease is going to be 97%. And the probability the test comes back positive given you don't have the disease, those false positives, would happen 3% of the time as well. Okay, so that's what that wording is telling us. And now ultimately we want, what is the probability that a person who tests positive does have leukemia? What's the probability the person actually has this leukemia? And what had happened? The test came back positive. So given the test came back positive. So we're going to be looking for the probability of L given plus, okay, the probability the person has leukemia given that they got a positive test result. So first and foremost, this is a conditional probability. So we start with our conditional probability for probability of L given plus. That's going to be the probability of L and plus divided by the probability of plus. Or in other words, the probability the person has leukemia and tests positive divided by the probability they tested positive. Now, up here in the numerator, okay, we draw on general multiplication rules, specifically the rule dealing with the and situation, which I just mentioned was the general multiplication rule, okay? And that is in one of the 6.4 videos if you want to go back and check that out. General rules of probability was the topic of that lesson, okay? But it shows you how to deal with these ands. Now, look, I don't know what that is. That's not given up here. None of that information is given up here. So what I got to do is use the general rule, multiplication rule to break this up. This is actually equal to the probability of plus given L times the probability of L. Okay? And again, go back and review that 6.4 video if you need to, okay? So that's how we use the general multiplication rule to break up the numerator, and we do that, and so, and like the trick is, look, if we're looking for this conditional, we always break the numerator up into the opposite conditional because that's what we have here, okay? Oops, and I think I used some wrong letters, right? I was talking about using the letter D, and I ended up using that instead of the letter L. Let me change those because I may have confused you. There, we're using L for leukemia here. There we go. So anyway, back to the point I was making. Look, we always take this and whatever it is we're looking for, we break it up using the opposite of that, okay? And again, that's information that we have. We have those values, okay? They were given to us. Now, in the denominator, we've still got to deal with the probability that someone tests positive. Again, that's not information that's given anywhere up here. We don't have that, okay? So this is called the law of total probability, okay? I believe it's a 6.5 lesson, or it might be the 6.6, but you can go and check. I do a couple examples with those. Now, the idea behind the law of total probability is this. Look, we got to find all the ways that the test can come back positive. Now, if you think about it, there's only two ways the test can come back positive. It comes back positive and the person has leukemia, or the test comes back positive and the person doesn't have leukemia, all right? So I can write that as the probability it came back positive and the person has leukemia, or plus the probability the test came back positive and the person doesn't have leukemia. And now in the denominator, we've got these two and probabilities to deal with. And we're going to deal with them much in the same way we dealt with the and in the numerator. In fact, this and this are exactly the same. It doesn't matter if you flip-flop the symbols when you're dealing with and. Probability of leukemia and testing positive is exactly the same as probability of testing positive and having leukemia. Okay, so the point is, what I did up here to get that, I'm going to do the same thing with this. So look, I'm just going to rewrite my numerator. I'm not really changing anything up top here in this step. But now this becomes exactly the same thing we already have in the numerator. And then this is going to look a lot like this, but instead of L, we're using not L. So it's going to be the probability we test positive and do not have leukemia times the probability we do not have leukemia. And I'm just running out of a little bit of room on the side there. So bear with me if I can't close that parenthesis properly. All right, but now every one of these values we have, okay, every one of these probabilities is stuff that was given. So that up in the numerator, let me just clean this up so I can better highlight as I go. So we're going to sum in for these values. The first thing I just highlighted, that's probably a plus given L. There's that 0.97. Times probability somebody has leukemia, that's 0.006. So there's our numerator down below. First term is, again, probability plus given L, that's 0.97, times, again, probability of L, 0.006, exactly the same thing that's up top. Probability of plus given not L, that was that 0.03, times the probability somebody does not have leukemia, 0.994. Right, then I would recommend punch the top in, and then punch the bottom in, and then do the division. Don't try to punch this all in at once. It gets kind of hectic with the parentheses you got to use. Punching in the numerator gives me that. Punching in the denominator gave me that for about 0.1633, which is choice B up there. Okay, and again, this is using the notation. Now, if you don't like the notation, there's another way to go through this. You can make a table, all right, which again is something I show in the Bayes' theorem lesson. So if you want to go through it that way, let me erase all this, all right, just to make some room here. We're still looking for this thing. This is still exactly what we want at the end of the day, okay? But with a table, we can at least come up with some numbers, and maybe it makes it a little easier to go through. So look, what I'm going to do is make a table now, a two-way table. And we'll have our totals, okay, and we'll have L and not L, so I'll use the side for that. This will be leukemia, does not have leukemia, and test positive, test negative. Now for this, you have to just make up some sample size. I like to use a big number like 1,000,000 because it usually works out nice, just to avoid using decimals ultimately. But you can really use any number you want, as long as you're comfortable using decimals if they show up, okay? But I'm going to use 1,000,000. Suppose we have 1,000,000 people, okay? Now, what do we know? We know that only 0.06 of the population is going to have leukemia. So I can come up with the total number of people who have leukemia, right? Here's leukemia. Here's the total number who have it, all right? And so to get that number, I'm going to take my population of 1,000,000, and I'm going to multiply by 0.006. And ends up being that 6,000 people out of the 1,000,000 would have leukemia. So I've got that number now, okay? Now, keep in mind what we're looking for. That's this divided by that, the probability of L and plus. I'm basically going to be looking for the number of people who have leukemia and tested positive. I want this number right here, divided by the total number of people who tested positive. Here's the total number of people who tested positive. So I want those numbers, I'll divide them, and then I'll get my answer, okay? So let's check this out. We got to work to get those numbers. So in any event, we figured out 6,000 people have leukemia because that's 0.6 of the population here, all right? Now, we can use some of these conditionals to get this value that we're looking for right in here, the L and plus, okay? So let's think about this. What does it say? It says the probability that the test comes back positive given you have leukemia is 97%. So what that means is of the people with leukemia, 97% of them will test positive. Well, of the people with leukemia, there's our 6,000 people who have leukemia, 97% of them are going to test positive, okay? And if you punch that in, you're going to get 5,820, 5,820. And there's the number we want in the numerator. So if a population of 1,000,000 under these circumstances, these given statistics, 5,820 of them would both have leukemia and test positive for it, okay? Great, so we got that. Now, ultimately, we want this total number who test positive. To get that, we're going to first have to figure out what this number is. Okay, let's figure out the total number of people without leukemia to test positive. Then we can add those two numbers, giving us the total, okay? So look, of the people, let's see, which one are we interested in? This right here. Of the people that don't have leukemia, 3% of them are still going to test positive. So if I know the number of people that don't have leukemia, then I can figure out what 3% of that is. And we can get the total number of people without leukemia. That's going to be this box right here, using this piece of data up here. Okay, out of our 1 million people, 0.994 of them, or 99.4% of them, are going to not have leukemia. Okay, so you can do the math there. You can multiply 1 million by 0.994, and you get 994,000. You could have also just subtracted the 6,000 from the million to get that number as well. Okay, but again, let's come back to this particular conditional now. Of the people that don't have leukemia, okay, of these 994,000 people, 3% of them are still going to test positive. So if I multiply those numbers together, I'm getting 29,820, okay? And so there, in this population, are the total number of people who will not have leukemia, but yet will test positive. And what do you notice? It's actually a lot larger number of people who test positive that don't have leukemia than do. And it just has to deal with the much larger number of people who don't have it in those false positives, just the way it works out, okay? But in any event, if we add those two numbers together now, we get 35,640. And so now coming back up here, we can punch those numbers in. So we've got 5,820 who have leukemia and test positive, divided by the total number who tested positive, 35,640. And what do you suppose you're going to get when you punch that in, folks? Well, again, you get exactly the same thing here. Okay, it works out exactly the same. So just historically, I know that students tend to prefer the table method. It gives you a little more context to what's going on and lets you better see the numbers that you're dealing with. Okay, but again, Bayes' theorem, in my opinion, the highest level of concept within Chapter 6. It really draws on a lot of all the other probability rules. And if you want to know the notational way of doing it, you really have to have a strong understanding of all those rules. Okay, moving on. Number 7. Given that the probability of A is 0.4, the probability of event B is 0.5, and the probability of A or event B is 0.6, the value of the probability of A and B is going to be what? Okay, so again, this comes out of the general rules of multiplication lesson, dealing with given any two events A and B, and we're really focused on the formula for the OR rule, your general addition rule. The probability of events A or B is given by the probability of event A plus the probability of event B minus the probability of events A and B. Okay, so that's the formula that connects all of these things here. And with that now, we can just sub in all the different values and we can solve for what we're looking for, which is the probability of A and B. So ultimately, I want to solve for this. Let's sub everything in. Well, they told us the probability of A or B is 0.6. Probability of A is 0.4. Probability of B is 0.5. And cleaning this up, that's going to be 0.9. All right, and so what do I have to subtract from 0.9 to get to 0.6? It looks like 0.3. So the probability of A and B, 0.3. One of these answer choices you should have been able to eliminate immediately. And which one would that be? Hopefully you're looking at A, right? Probability is always between 0 and 1, never greater than 1. Okay, but in any event, this one ended up being 0.3. Okay, general addition rule. Okay, number 8. A survey asked 75 students if they thought gangster rap should be banned from being played on any radio stations. The results of the survey are shown in the table. Find the probability of n given m. Okay, so the probability of n given m, again, this is a conditional probability, so by the formula, it's going to be the probability of the and, so probability of n and m, divided by the probability of the thing after this little line here, always. So divided by the probability of m. And the nice thing with the two-way tables, as we saw in the Bayes problem, is that we can now just pick up the number of people in the population. So in the numerator, n, no, and male, that was that 15, divided by the total number of males, that's 35. Both are divisible by 5, so that simplifies to 3/7 or choice B. Okay, number 9. In a particular school, students take one of math, chemistry, or physics, and one of history or drama. The choices are shown in the table. What is the probability of 3 decimal places that a student selected at random is taking math, given that he or she is taking history? Okay, so I'm going to use M for math and H for history. So here, again, we're looking for a conditional probability. What's the probability they're taking math given they take history? But instead of being given to you notationally, this time it was given to you in words, and you had to put it together. So probability of M given H is going to, again, be the probability of M and H, this time divided by the probability of H. How many students both take math and history? There's 94, divided by the total number of students who take history, 235. Punching that into your calculator, you get back 0.4 on the nose. Okay. Another conditional probability coming up, but this time you were given more information than you needed, and your job was to just use what you had to. So again, probability of A given B is going to be the probability of A and B divided by the probability of B. Probability of A and B is given. Probability of B is given. Probability of A is given, but we don't end up needing that. Okay? You can punch that in carefully. You can keep, change, flip if you want to divide by fractions. Okay, whatever you got to do there. I'm going to simplify, and we get back 11 over 39, which is choice D. Okay, and then last but not least, this is one that I got quite a number of emails about. The correct choice is here. Hopefully it'll make sense after going through it. Okay, again, this is Venn diagram stuff. There's a worksheet that I posted for you guys and a video I go through doing numerous examples from that worksheet, one of which is pretty similar to this problem, okay? So to determine which restaurants are liked in the city of Freeport, a survey of 100 residents was taken with the following results, okay? 62 of those 100 people liked Judy's Joint, 47 liked Lou's Lobster House, 32 liked Frank's Fish House, 17 liked Frank's and Judy's, 20 liked Judy's and Lou's, 12 liked Lou's and Frank's, 5 liked all 3 restaurants. How many liked Judy's Joint in neither of the other 2 restaurants? Okay, let's set up a Venn diagram for this. Okay, so we've got 3 circles. And they overlap because what we're going to do in these circles is represent the restaurants. There's Judy's, there's Frank's, and there's Lou's. Okay, so I'm going to label them J, F, and L. All right, and they gave us the number of people who liked these restaurants. Now, look, what you can't do is the following. Right, 62 like Judy's Joint. Okay, so I'm going to put a 62 there, right, and then a 47 like Lou's. This is incorrect what I'm doing right now, okay? Look, if you do that and you start like, okay, 17 like Frank's and Judy's, so I'll put the 17 there, 20, okay, so on and so forth. Look, if you add those numbers up, you get a number that's a heck of a lot bigger than the 100 residents we're dealing with, okay? So that's not, like 62, if you put the 62 there, that's saying 62 people liked Judy's, but not the other 2 places, right? So we got to be really careful about how we go about setting up these Venn diagrams given this information, okay? 62 people like Judy's Joint means that in the total of this circle, it's going to add up to 62, but that accounts for the whole circle. All right, so the trick here is, look, you got to start with the innermost intersection to start getting the numbers in this place correctly. 5 people liked all 3 restaurants. That's an easy number to drop in there. 5 is in the innermost intersection. There's the 5 people out of the 100 that liked all 3 places. Let's talk about the 12 who liked Lou's Lobster House and Frank's Fish House. If you look, the intersection of Frank's and Lou's is this right here. All right, there's the intersection. So when they say 12 liked both, that means that the total of that pink region has to be 12. All right, not this. This is not 12. Okay, the total of that region is 12. So think about it. We've already accounted for how many people in the intersection, 5. So if a total of 12 is going to be there, what's the math going to be? We're going to do 12 minus 5. That leaves us with 7 people in this region right here. All right. And so basically, we're going to continue with this process of subtracting to get the numbers that we need in each region. So let's move on. 20 like Judy's and Lou's. Judy's and Lou's is this intersection. We've already accounted for 5 of those people, so 20 minus 5 is going to leave us with 15 in that portion. 17 liked Frank's and Judy's. That's where Frank and Judy intersect. 17 minus the 5 we've accounted for leaves us with 12 in that portion. Now we're going to continue on and see what we get here. So 32 liked Frank's Fish House. So all of Frank's is going to add up to 32. Okay, this whole thing adds up to 32. Well, we've got 3 numbers to subtract there. Okay, so 32 minus the 12, the 5, and the 7 we've already accounted for. And that's going to leave us with 8 people who liked Frank's. And that's 8 people who liked Frank's and not the other 2 places, right? They're only in the Frank portion of that circle. Okay, up here, 47 total like Lou's. 47 minus what we've already accounted for, 15, 5, and 7. That leaves us with 20 people who liked Lou's and not the other. And finally, we get to Judy's. 62 total people like Judy's. 62 minus the 12, the 5, and the 15 is going to leave us with 30 who liked Judy's, but not the other 2 restaurants. So choice B it is. All right, folks. So work on that. And if you have any questions, please reach out. Okay, you're going to have another opportunity at a quiz on this stuff. So hopefully it goes a little smoother. Okay, have a great holiday, folks. And